Hi there. Thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley. It's good to have your company. Today, we will be hearing questions about the universe being inside a black hole. In fact, I think they're suggesting it was born in a black hole and is stuck in there, and how do we get out? We'll also be looking at a new gravity theory, Hubble tension. Not surprisingly, questions about Planet 9 with the most recent announcement of something being out there that's not Planet 9, and getting gravity assistance to max delta V. Those are all the questions coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And Fred Watson is with us again to solve all these little riddles. Hello, Fred.
Hello, Andrew. Nice to help you solve the riddles.
I don't know anything. That's why I bring you along.
Oh, good. Well, I'm glad to be of assistance.
Makes it so much more interesting when there's two people talking. Monologues are just so boring, don't you reckon? Unless it's a super interesting person like yourself, Fred.
No, I'm capable of boring the pants off people, as people have assured me before, so that's all right.
So we've got a lot to get through, and it's even trickier this week because we do have a technical issue, which means you are going to have to lip read.
Okay. So, right, I'll do my best.
We'll see how that goes.
Just wondering where the lips are going to be. That's the only thing.
Yes. Well, the first set of lips come from Paul, so let's hear his question.
G'day, Fred, Andrew, Jonty, Heidi, whoever happens to be at the helm. This is Paul from sunny Brisbane, Vegas. Thanks for doing a great job as always. I have a quick question about, surprise, black holes. Dr. Shamir put out a paper recently about his ideas regarding the fact that some galaxies are spinning one way and a lot of them, most of them, the other way. And another fella chipped in, Nikodem Poplowski from New Haven, suggested that maybe that was because our universe was born inside a black hole. If that is true, how the heck did we get out? And if we didn't get out and we're still inside, then how is that possible given that, anything that goes inside a black hole is spaghettified, according to our current thinking, and therefore incoherent? I mean, I know I'm incoherent, but you know what I'm talking about when it comes to ordinary baryonic matter. Love to get your thoughts on this. Anyway, keep up the good work and catch us later. Cheers.
Thank you, Paul, and hope all is well in Brisbane. Paul is asking about the universe being born inside a black hole. How do we get out, and why don't we get spaghettified as a consequence of that, amongst many other things? But that was the basis of the question.
So as you've already mentioned, I didn't hear any of Paul's question there. Not at all. However, I did listen to it yesterday, so I've got a bit of an idea of what Paul was suggesting. The fact that we have new observations which have been made with the James Webb Space Telescope that are intriguing in the sense that these scientists, and they are basically mostly located at Kansas State University, the rotation of galaxies in the deep universe isn't random. You'd expect, galaxies to be rotating in, they can only go one way or the other, but you would expect an equal balance of rotations. And what we find, or what these scientists find at Kansas State University, using the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES, what they find is out of 263 galaxies, which sort of give away their rotation, because we know that spiral arms nearly always trail. There's at least one galaxy where the spiral arms are leading, but most of them trail. And what they find is that out of these 263 galaxies, about 2/3 of them are going clockwise, and the rest are going anti-clockwise. And that is an imbalance. That's a statistically significant imbalance that suggests that something's going on that we don't understand. And that leads to the possibility that perhaps the universe itself is rotating. And I've seen other papers on this topic that suggests that maybe the universe rotates once in every 500 billion years. That's one figure that I've seen. Now, a consequence of the rotating universe, and I think this is where Paul's question went, I'm trying to remember having heard it yesterday, is that it lends some weight to the idea that the universe is inside a black hole. In other words, that there is an event horizon at some huge distance from where we are, and we are all within this black hole. What does that mean for observational cosmology? I suspect it's going to be very difficult for us to confirm that ever. I think, this is speculative research. It's important research because you want to know how some of these things interact. And I might just mention, and I think we've discussed this before, Andrew, on Space Nuts, that the idea of a rotating universe actually relieves some of the issues that we find in observing the universe. One of them is the Hubble tension, and I know there's a question coming up about that. So a rotating universe has certainly attractive possibilities, but we absolutely don't know whether it is a rotating universe and indeed whether that means that we're inside a black hole. So what I was going to say was the idea of a universe within a black hole is akin to the idea of multiverses, the idea that multiple universes exist and we are just one of them. I don't think giving a sensible answer to Paul's question, partly because I couldn't hear it, but I think he was basically asking, what happens? How does it happen? How are we not being spaghettified? That's because I can tell you the answer to that. We're not in a region of the black hole where the gravitational pull is changing very, very rapidly with space. And that's what makes a black hole spaghettify you. You go from one point to another and your gravitational pull is very different. So your head feels a different gravity from your feet and you get spaghettified. We're not in a place where that would be happening if we were inside a black hole. But, all bets are off because inside a black hole, we're in a different dimensional space. A black hole is a singularity. Are we in a singularity? A singularity is a point with no dimensions. Work that one out. So we'd have to be almost in a different dimensional space. So it's an interesting question to which I don't think anybody knows the answer, but there are a few people who are probably thinking through it a lot more clearly than I am.
Well, Paul mentioned a physicist by the name of Nikodem Poplavsky.
Yes.
He's one that's put this theory forward that our observable universe is not just a part of a larger universe, but is in fact the interior of a black hole within a larger context.
Yes, so you've got extra dimensions somewhere out there within which we exist. That's right. It's yes, I remember checking out the researchers that Paul mentioned yesterday when I looked at it. It's interesting stuff. Yeah.
What do you think personally? I mean, is there any possibility that this could be real?
To me, it's on the same level as does heaven exist? It's questions to which we really can't find answers. We can theorize, we can conjecture, we can speculate, we can write equations down, and probably some of the equations do support the idea that we're within an event horizon. It goes back a very long way. It's not a new idea at all. But people have put new numbers on it, I think, and new observations. I think we watch this space. Next time this question comes up, I might be able to hear it properly and might be able to give a more cogent answer.
Yes, indeed. I'll be working on that technicality.
I'm sure it's not your fault, Andrew. I know what these gremlins are like. We get them all the time.
Yeah, I'll blame the equipment. Never, ever
never the person using it. No, that's right.
Thank you, Paul. Hope we covered that adequately as we strive to do here on Space Nuts. Let's take a little break from the show to tell you about our sponsor, NordVPN. Now, I've told you about virtual private networks many, many times. I use them myself. In fact, I use NordVPN, and I did pay for it. So I feel even more qualified to tell you what I think. And I've used it overseas recently, and it works. It's one of the most trusted and widely used VPN services in the world, and for a very good reason. It encrypts your data, it hides your IP address, it makes you much harder to find online from anybody trying to steal your passwords, steal your usernames, sell them on the dark web, or just get into your bank accounts and clean you out. Whatever their motivation, it's not usually very good for you if they succeed. But the way to protect yourself is with NordVPN, top-tier security. And we're talking about the same standard of security trusted by governments and cybersecurity experts. They have a global network. They've got thousands of servers in over 60 countries around the planet, and no geo restrictions as a consequence of that. And very fast speeds. In fact, I have actually experienced higher speeds connected to my VPN at home compared to what I'd normally get from my internet service provider. I don't know how that happens, but it certainly has happened a few times. They have a strict no-logs policy, which means they don't track or store your browsing history. And they offer all sorts of other tools like threat protection, dark web monitoring, and a kill switch for added safety. Now, if you'd like to find out more, there are discounts at the moment for Space Nuts listeners, and it's really quite simple. Just go to nordvpn.com/spacenuts. That's nordvpn.com/spacenuts. And then you click Get the Deal. Don't forget they've got a 30-day money-back guarantee. And you can get an extra 4 months free by signing up as a Space Nuts listener. So click on Get the Deal. They have plans that you can pay monthly, or you can go a year in advance or 2 years in advance. And the longer you sign up with them, the better the discounts. So go to nordvpn.com/spacenuts for your online security today. And don't forget the code word spacenuts at the checkout. nordvpn.com/spacenuts. Click Get the Deal, and then have a look and see what suits you best. Now, back to the show.
0G, and I feel fine.
Space Nuts.
Our next question, Fred, comes from Casey in Colorado. In fact, he has two. Could you please explain the new theory of gravity in simple terms? Does it have any merit? And could you please explain Hubble tension and what it means for our understanding of the universe?
Yes. So
that's the answer.
The answer is yes. Yes, I can. The new theory of gravity, which I like very much, this comes from scientists in Finland, which is a place that I like very much as well. And it's what they've done. They've taken a step forward, and I'm assuming this is indeed the new theory that Casey's speaking about, because we get nearly one every week, a new theory of gravity. But this is the latest one. It's as I said, it's from Finnish scientists at Aalto University. So it's what they've done is what Einstein tried to do for the last 30 years of his life, which is to unify quantum field theory and relativity. And that's an issue because they are incompatible at the levels that we try and look at them now. And so to bring a quantum theory of gravity into being is a big step. So what do I mean by bringing a theory into being? Well, we know that there are four fundamental forces in nature: the strong and weak nuclear forces, electromagnetism, and gravity. And the first three of those have very, very well established and well understood quantum theories. For example, we know that electromagnetism is propagated by photons. We're talking about it all the time. So the suspicion is that gravity is propagated by gravitons, but so far there's been no theory of what gravitons might be like. So what these scientists have done, have developed a new theory, a new quantum theory of gravity. And I'm actually going to once again quote from phys.org, a very nice account of this, which is actually, I think it is part of the press release from Aalto University in Finland. So I'm quoting the university. Researchers at Aalto University have developed a new theory, quantum theory of gravity, which describes gravity in a way that is compatible with the standard model of particle physics, opening the door to an improved understanding of how the universe began. While the world of theoretical physics may seem remote from applicable tech, the findings are remarkable. Modern technology is built on such fundamental advances. For example, the GPS in your smartphone works thanks to Einstein's theory of gravity. And then the article goes on to describe the theory is published in research reports on progress in physics. And this is the quote that I wanted to make. This comes from the lead author of the paper. Basically, they've got lovely Finnish names. That's why I'm stumbling. It's Mikko Partanen, who's the lead author, and the quote is as follows. And this kind of puts it into perspective. If, that's the big word, if this turns out to lead to a complete quantum field theory of gravity, then eventually it will give answers to the very difficult problems of understanding singularities in black holes and the Big Bang. A theory that coherently describes all fundamental forces of nature is often called the theory of everything. Some fundamental questions of physics still remain unanswered. For example, the present theories do not yet explain why there is more matter than antimatter in the observable universe. And what they've done is they've developed something called a gauge theory. And gauge theories are a particular kind of theory about the way particles interact with each other through a field, like the Higgs field and the Higgs boson. So it's basically a very nice account. I won't read any more because the gauge theory's got symmetries and things of that sort. It's a nice account. I recommend people have a look at the phys.org paper. The phys.org article. Casey, I'd send you to that as well to have a look. It's a very nice account of what's happening. You may end up like me thinking, I really need to know a bit more about gauge theory before I can understand this. But nevertheless, you'll get a good idea of what's going on, I think.
Okay. Now, Casey also wanted you to explain, if you could, Hubble tension.
Yeah, that's an easier one. And as we've spoken about...
That's good.
As we've spoken about today, that's one of the things we might get rid of. Yes, Hubble tension's a lot easier than gauge theory. And what it amounts to is we've got two ways of calculating the current expansion of the universe. One is by looking at galaxies in our vicinity and looking at the rate at which they are speeding away from us. They're moving away from us faster as their distance increases. This is exactly the discovery that Hubble made in 1929. And it gives us something we call the Hubble constant, which is just the rate of expansion of the universe today. We call it h0. Hubble 0, which is the expansion rate today. Now, you can also get an idea of that or a measurement of it from the cosmic microwave background radiation. And that, to recap, is the flash of the Big Bang. We're looking back so far in time. We're seeing back to a time 380,000 years after the Big Bang when the universe was still opaque and glowing brightly. So we see this wall of radiation, which is now in the microwave region of the spectrum. And it's peppered with a pattern of warmer and cooler places. And those zones of higher and lower temperature, and it's only by a tiny fraction, they correspond to the structure in that fireball. In fact, that is caused by sound waves moving through it. They're called baryonic acoustic oscillations. And we can, by measuring the properties of that peppering of warmer and cooler regions, we can actually work out what the expansion of the universe is today. And it turns out that the two figures are different by something like 4-5%. And that, in modern terms, is big enough to worry about. It's not just an error of measurement. These have got fairly tight limits on the uncertainties, but they're different. And that is the Hubble tension.
But didn't they recently release a paper that suggested that the variations are actually within a normal range, that these two figures that don't match are close enough?
Well, yes,
didn't we talk?
We did.
That?
Some people have suggested that it is actually within the experimental uncertainty, but it's still seen as a tension. They should be nearer than what they are.
Yeah. Okay. Very, very interesting. Casey, thanks for both your questions. And no, you haven't spammed us. 2 questions doesn't equal spam. There's probably a definition somewhere online that says how many emails become spam. You're well outside that tolerance, so no problem there. This is Space Nuts Q&A edition with Andrew Dunkley and Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Okay, Fred, let's move on to our next question. It's an audio question, so you won't be able to hear it, but it comes from Simon.
Hi, it's Simon from Vasey in New South Wales here. My question's around the search for Planet 9. Other exoplanets, a few have been found using radial velocity method. Is that something we could do with the Sun? I guess Planet 9, being so far out, probably wouldn't have much influence, but we would have so much data on the Sun as well. That it might be easy to suss out. Anyway, that's my question. Thanks for the show.
Thank you, Simon. Good to hear from you. Hope all is well in Vasey in New South Wales. He's asking, in the search for Planet 9, we've used the radial velocity method in the past to find other objects. Could we use the Sun in the search for Planet 9?
Yeah, and it's a great question. And very well posed, Simon. I did actually manage to hear that through my own recording, which I found and listened back to, so I know what Simon asked. Okay. And what he's saying is that we know that when we look for exoplanets, planets around other stars, what we look for is the change in position of the star itself as it's pulled one way and another by the planet orbiting around it. And yes, indeed, the solar system has such an effect. So Jupiter principally is the main planet that's pulling the sun's center one way or the other. But the other planets all intervene as well. And so what we have is something that's called the solar system's barycenter, the center of mass of the solar system. And that moves as the planets wander around. And we've, exactly as Simon says, we've managed to work out the position of the barycenter very, very accurately, partly because we know where the planets are and things of that sort. Now, Simon's question is actually exactly the same as a question that I found on Stack Exchange online. The question was,
wow,
can the paper narrowing the solar system's barycenter to within 100 meters help find Planet 9? So that's basically what Simon asked. And the bottom line, there's a long set of calculations here, which I won't go through, but the answer is probably not. It's because the Planet 9's influence on the solar system's barycenter, it's helped by the fact that Planet 9's a long way away. So it's got sort of leverage as it goes around. The short answer is maybe we could do it, but we wouldn't be able to do it without hundreds, if not thousands of years of precise data. And that's because Planet 9 is probably orbiting the Sun on that kind of timescale. And so you don't see any what you'd be looking for is changes in the position of the barycenter, which are not caused by the known planets, but it'll take you hundreds or thousands of years to see that because of the great distance that Planet 9 is at. So the answer is probably not, but it's a great question and really nice thinking. I like Simon's thinking there.
Yeah, it's quite astute. The other factor that comes into play here is the new theory that Planet 9 doesn't exist because there's another planet even further out that has only just been sort of put into a paper and open for discussion. So we only talked about that last week. So the search for Planet 9 might be a forlorn hope anyway.
Yeah.
Because it probably, according to the new theory, doesn't
That's
exist.
correct, yeah. Now, the new theory is based more on observations than theory because it's two observations separated by something like 30 years that seem to show something moving very slowly in the outer solar system. You can bet your life we'll do more observing of that over coming decades, and maybe that will turn out to be what I think is being called Planet 8.5 at the moment because nobody really knows whether it's there or not. But as you said, if that is real, it rules out Planet 9. The two can't exist together.
Exactly right. All right. There you go, Simon. We'll see where that ends up, but it might take a while. Final question comes from Joe in Olalla in Washington. I hope I pronounced that correctly. Is there an upper limit to how much delta V that can be practically generated by gravitational assists? Is it possible to develop sufficient delta V for timely interstellar travel by winding up a probe in our solar system before launching it to a nearby star? Thanks for all that you do. Cheers, Joe. Now, delta V, that is the impulse per unit of spacecraft mass.
Yes. Well, it's basically the change in velocity.
Yeah.
Yes, and impulse is that's the way people talk about these delta Vs in the rocket industry. It's all rocket science. What is it? Anyway, delta V, I think in Joe's context here, is how much velocity increase you can get from a gravity assist, from a slingshot. And the answer is probably no, in terms of trying to wind up, the speed of things so that you hurl something out of the solar system at 10th the speed of light or something like that. The reading that I've done on this, and I did check it out, seems to suggest, excuse me, that we are probably limited to the sorts of velocities that we see among the planets of the solar system. Now, remember, the Earth is orbiting the Sun at 30 kilometers per second. And those velocities get less as you get farther away from the Sun. And that's part of the equation with a slingshot, because what you're trying to do is steal some momentum from the planet and give it to the spacecraft. And so there are upper limits on what sort of velocity change you can get. It depends on how close you go to the planet. It depends whether the planet's got an atmosphere or not. It depends on the angle that you come in. The figure that I've seen quoted as a maximum for Jupiter, which is the most effective planet for this sort of thing, being by far the most massive planet in the solar system, is a change of 40 kilometers per second. Now, that's very good if you're, trying to get something out to the outer solar system, but it's not going to help you getting things to other planets, especially when you think, if you give a spacecraft an impulse, a delta V of 40 kilometers per second by interacting with Jupiter, you've got to then find another planet that's going to give it even more, but the other planets are all moving slower than that. So that the change in momentum is a lot harder to get. So I think the answer is, it's a very nice idea, as Joe suggests, winding up by all these gravitational interactions. You can only do it within limits. You're not going to be able to get, like 100,000 kilometers per second or something like that from doing that.
Yeah, I suppose that you could equate it to using a slingshot or a Shanghai. There's only so much tension you can put into the rubber band, to fire the rock, and you're not going to be able to fire the rock any faster than the maximum amount of storage the rubber band can hold. And I'm guessing it's the same for.
Yes, there's a limited amount of energy that you can get from a slingshot. That's right.
Yeah,
Nice idea there.
although it's been very effective, as you said, for sending things to the outer solar system. The Voyager probes particularly used the slingshot effect several times to get to the outer solar system, because they didn't have the fuel to do it. So they figured out through an alignment of the planets that they could get out there just by using the rotation of the planets, or the process that Joe's been talking about. So it does work quite effectively for slower speeds. But interstellar, probably beyond us in that regard.
Yeah, probably the lasers and and a solar sail or a light sail might be a better bet. But even that's beyond our technology at the moment.
Probably won't be for long, though. I think they'll develop that and get some spacecraft heading out towards the Alpha Centauri sector. And anyway, that remains to be seen. But that would still be a pretty slow mission in the scheme of things. But great question, Joe. Thanks for sending it in. And if you'd like to send us a question, you can do that through our website, spacenutspodcast.com, spacenuts.io. Click on the AMA link at the top, and you can send us text and audio questions. And don't forget to tell us who you are and where you're from. We love to know that sort of stuff so that we can send the boys around. Or we could send Hugh around, because he can't be with us today, so he must be visiting one of you guys with his balaclava on, maybe. Yeah. Thank you, Fred, as always.
A pleasure, Andrew, as always. Good to talk, and good to hear our listeners' questions.
It is. All right. Well, catch you again real soon. Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks for your company. See you on the next episode of Space Nuts. Bye for now.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.